Hi everyone, so I'm now showing it's 1:30, so we will start off this meeting. So welcome everyone. I'm sure we're going to have a few more people join us as we start. It always seems to take a while for people to get Teams especially working and to click on the right buttons. So I'm sure more people will be joining us as we go through. But since it is 1:30, we will start this little webinar now. So first of all, welcome to everybody. My name is John Horden. I am the CEO of iKVA. And with me, I have Professor Richard Mortier, who is the CTO of iKVA and also Professor at Cambridge University as well, who will be doing most of the talking on this, which is a voyage into discovery to really introduce how vector search is a new technology that is kind of sweeping the world in terms of understanding language and how this can be applied into various situations. Just a few housekeeping rules just to start off with. So everybody should be aware that everybody's coming in on mute for this conversation. This is going to be a Q&A session. So there's going to be around 45 minutes of more going through exactly what vector search is and its applications associated with that. And then we'll follow that up with questions and answers. So if you do have any questions, please use the chat window. So everybody should have access to the chat. So you can ask questions in that chat and then we'll answer them at the end of the session. Just one more thing to be aware of, this session is being recorded. So if you want to pass the details of this session on or you want to re-review it, this is recorded. So we'll be able to distribute that recording to everyone, and feel free to pass that on to anybody that you want to that may be interested in this. So really, without further ado, let me introduce Professor Richard Mortier, or Mort for short. Mort, would you like to take us into a voyage of discovery, please?
Sure. Thanks, John. So as John said, what I'm going to do is sort of talk through a little bit about the technology that we use in iKVA, how that works, and how we've kind of put it all together. Just very briefly as a piece of background, so iKVA is a startup. We're an early stage AI knowledge management company. We come out of research from the Cambridge University and the ATI. We're based in Cambridge, UK, and we are basically building a platform that enables next generation knowledge management. So the aim here is that we want to enable organizations to access and gain insight from all their knowledge, and that helps to cut costs, reduce risks, and basically getting the right information to the right people at the right time. And so what I'm going to do is talk a little bit about how we do that and how our platform works. This is the agenda. So I'll go through sort of the problem setup, if you like, how we conceive of the problem that we're trying to address. Then I'll talk through some of the technology that we built to address that. So document extraction, document embedding, vector search, so vector indexing, and then integration and how we can integrate this to capability into different workflows and tools. And then there'll be some time for Q&A at the end, as John says. So to start out, the problem that we're trying to address here is really one of discovery, not search. So what we've observed over the last couple of years, we've kind of honed in on this as we talk with more customers, is that there's an essential difference here between these two processes. Search is quite a targeted activity. So typically you're in a situation where you know there's a document that's got the information you're looking for. You know there's something in the data set and you're trying to find it. So what that kind of means, what that entails, is that you've got some prior knowledge of the target result that you're looking for. And you're probably going to engage in a kind of repeated querying process where you iterate towards a solution. So you might type in a question, a phrase, you might type in a few keywords. You'll get some results back. You look at those results. It doesn't quite contain what you're looking for. So you tweak the query a little bit and you're moving towards the solution that you're looking for. It also means that there are some inherent biases in this because you're coming with prior knowledge of what it is you're intending to find. So there may be other information in the data set which is actually quite relevant to what with the problem you're trying to solve, but you simply won't go looking for it because you don't know it's there. In contrast, discovery, and that's what our platform is trying to support, is a much more exploratory activity. So it's more the kind of thing where you're in the middle of doing something already, and you need to know things that are relevant to that activity that you're already carrying out. I guess we'd observe that in a lot of knowledge work, most knowledge work, there's some kind of text or document that you're using in the course of that work. So it might be something you're reading or something you're writing, a conversation you're having. There are some words associated with it. And so discovery is a process of really taking that context and almost issuing a one-shot query where you just use that context to try and find the relevant content. So you're not going to do this iteratively. You're not consciously constructing a query in order to go and find something. You're simply using a representation of what it is you're currently doing to try and bring the right information to you in that moment, sort of at that point in time. We focus on discovery rather than more traditional enterprise search. What this means, if you can solve this discovery problem, is that you get access to the information inside the organization that you didn't know existed. This means that, for example, a common interaction that we have is people are talking about the problems of having large collections of data inside an organization, many different documents in many different silos. And essentially, the way that things are found is through the experience of the employees. So some employee knows that something was done in the past in a particular way, or a previous tender response was written, or a project proposal was written, and they kind of know it's in there. And so they use a search facility to go and find that thing, and they pull it out, and that's how they then can make use of that past information, the sort of historic information in the company. With a discovery approach that we provide, you don't have that problem. You can just pull out everything that's relevant. You didn't need to know it existed. You didn't need to try and construct a query to find it. It's simply being fed to you based on what it is you're currently doing. It also means that you get better quality and relevance of results because you're using a lot more information in the query. Instead of typing in a couple of phrases or a few keywords, you may be using an entire document. So it could be many pages of information that describes what it is you're currently doing. The way our platform works, I'll talk about this towards the end and when I talk about the integrations and extensions, we can provide results to you proactively. So you can get the information you need, again, without having to stop what you're doing. It just comes to you in whichever tool it is you're using. And I won't say very much about this, but there's also a nice feature here because of the way that language embeddings work, that you can do this across different languages without needing to do machine translation as such. So this is the overview of the platform, and I'm going to go into essentially these sort of three phases in the platform one by one. On the left, we've got data ingestion. So we can take source data from lots of different data sources, so long as there's text associated with it. So fairly obviously, that might be files, PDFs, Word files, PowerPoint decks, things like that. Perhaps less obviously, lots of forms of speech, whether that's speech on an audio call, video call like this, whether it's podcasts, whether it's videos from YouTube. We have a small data set of YouTube videos that we use as a demo, about 90,000, where we can take the transcripts of that information. It's essentially speech to text is now basically commoditized. So you can take the transcript of that sort of data, convert it to text, and then you can just treat that as another document, treat that as another input source of text. We can also work with chat sessions. So things like Teams, Slack channels, things like that, where you've got sequences of messages coming in. I'll talk a bit about how we can deal with that in a second, but essentially we can treat that as a source of text as well and take that into the system, index that and make that also discoverable. So we have all these different source data types and sources of data. What then happens is that data comes into our core platform, and essentially we go through a process there where we take that source data and extract documents from it. We take those documents and represent them as vectors, as high dimensional vectors. And we then build what we call knowledge packs. So that's essentially the collection of high dimensional vectors plus some indexes that allow us to do so-called approximate nearest neighbours search very efficiently. And we take all that collection of information, the indexes and the vectors, and any metadata that you wish to attach to those vectors. So the vector itself just encodes the content of the document. It might be useful, it is useful in most cases to perhaps include also a URL, attach that to the vector. So you can get back to the original document. You might also choose to include a title, a summary, things like that. So you take that collection of those three things, the vectors, the indexes, and the metadata, and that gives you a knowledge pack. And we then have the ability to query those knowledge packs by essentially running the same process again, but for a query document. So some query text comes into the system, it's converted to a vector, and we can then use those indexes to look for the nearest neighbours in that data set, in that particular vector space. And those nearest neighbours, because of the way those vectors are constructed, will be the documents that are most closely related to the query. And that's kind of the way that this whole process works. Data is taken in and ingested to build knowledge packs. We then query those knowledge packs to find the most highly related content. The system is quite fast, so we can deliver results in real time across millions of documents. We'd normally be looking at tens to maybe small 100 milliseconds for a query response. The indexing speed is pretty quick, and sort of as a concrete example, we take something like Wikipedia dump, which I think was about 6 million pages last time we did it, and we'd expect to be able to process and index that in something like a few hours. So that's the kind of the rough query rates and ingestion rates we're able to deal with. So that's a kind of very brief, very quick overview of our platform and the sort of problem we're trying to solve with it. So it's not a traditional search per se, it's this discovery process. So what I'll do now is I'll talk through some of the technology we use in the different phases in this platform. Beginning with extraction. So as I mentioned, we've got text is really this kind of common denominator for all sorts of knowledge work. And when we're doing that kind of work, we're typically reading, writing, talking, we're using words in some way. Documents, therefore, the way I'm going to use this terminology is documents can come from all kinds of sources of text. So documents might come from PDFs, Word files, presentations, PowerPoint decks, but we can also construct documents from the text that we can extract from things like audio calls, video feeds, chat sessions, and so on. For files, for example, you might want to segment a file into many documents. I'll say a little bit about that in a second. Calls to videos, as I've mentioned, speech to text is commodity. You can just take the transcript and treat that as some text. And then chat sessions. We have this process of disentangling the sequence of messages in a chat session. So, for example, in a Slack channel, to build multiple documents that can then focus on the distinct topics that were being discussed in that channel, possibly being discussed kind of overlapping each other in an interleaved fashion. First off, segmentation. So simply returning a long document as a result and saying something in this document is relevant might not actually be that helpful. When we first started looking at data sets and we were using, for example, academic papers or patents, that's not so bad. There's sort of reasonable units to think about. So you say this patent is relevant to your query, that's usually a useful response. When we started working with customers where we were dealing with rather bigger documents, so for example, strategic frameworks, government level frameworks, those might be many hundred pages long and covering all sorts of different topics in a very kind of rich document. So it's not very helpful to say something in this 650-page PDF is relevant to your query. So instead, what we look to do is we take those documents and we segment them when we ingest them. So we're going to treat each segment independently, although typically we would maintain metadata that matches the segment to the parent document, because it may well be useful in the user interface that we build around that to be able to say these 3 paragraphs are the particularly relevant paragraphs, but they come from this original document. And so if you want to get the bigger context there, you can go back to the original document. There's lots of different bases on which you might choose to do segmentation. So you can do it orthographically based on the properties of the text directly, based on paragraphs, sections, chapters. You could do it rather more simplistically on perhaps fixed length. So you simply segment your document into multiple fixed length segments. You might do it based on the particular properties of the input text or even the properties of the queries that you're going to execute. We focus on paragraph-based segmentation. We're trying to provide a platform here which is quite generic and quite able to be used for lots of different sorts of application, lots of different sorts of document. And paragraph-based segmentation is quite straightforward to implement. It's really quite efficient and it's very widely applicable. It's useful in quite a lot of different contexts with lots of different sorts of input data, input documents. We can then, so we start out that as a very simple approach. Take a document and split it up into paragraphs. It's then desirable to optimize that, where you essentially want to look at coalescing subsequences of paragraphs on effectively the topic shift. So rather than having each paragraph treated completely independently, you might want to say, well, this paragraph is very similar in terms of the topic that it concerns to the previous paragraph. And then the third paragraph is very similar to the second paragraph. The fourth paragraph is perhaps shifting around a bit, and by the fifth paragraph, you're looking at something completely different. And so you would therefore want to perhaps coalesce those paragraphs so that you create segments, documents, which comprise perhaps the first 3 paragraphs would be one document, and then the fourth and fifth paragraphs might be a different document. It is possible also to incorporate other forms of information, perhaps author-provided information, such as sectioning, chapters, things like that. It generally doesn't seem so helpful in practice. Usually this kind of topic shift approach is kind of good enough on its own. And again, because we're trying to build something which is widely applicable and can be used for lots of different applications, it's quite desirable to not try and do too many special cases in this. So an example of the sort of algorithm here that's been published many years ago in the literature, text tiling. So that's essentially you tokenize and you determine blocks in your document. You then compute similarity scores for adjacent blocks, and the block boundaries are the depth of the valley in the similarity score. So when you've ended up with a sequence of paragraphs which have started to differ, so the similarity score has started to reduce, and then you get into a region where the blocks are starting to become similar again, so the similarity score is increasing. So you've got this kind of dip and then back up again, and it's that valley that gives you the idea, the point at which you might choose to segment and separate one set of blocks from a different set of blocks. As I said, we're trying to be very general and very widely applicable in what we do. So the common implementation of this does rely on having clear paragraph boundaries so that you can do that effectively. but those aren't always available depending on the type of data you're dealing with. Query data, when we deal with it, could come from lots of different places. It might be a PDF, it might be a Word file, lots of different sources. So an alternative approach that we've looked at is using vector embedding again. So here you might take each line of text and embed that. So you create a vector that represents each line of the input text. You can then coalesce adjacent lines into paragraphs based on a similarity threshold that you would set between the lines in the current paragraph. So you're essentially looking at each line in turn and saying, is this close enough to the previous lines that it needs to go into the same paragraph as the previous lines? There's lots of different ways that you might choose to do that. So you could represent a paragraph, perhaps by recomputing the vector every time you add something to it. So you're creating a new vector each time as you added more text into the paragraph. Equally, you might choose to do something with the vectors directly. So you create a vector to represent the paragraph based on the average of the line vectors, of the vectors for each line in the paragraph, or the weighted average, perhaps. That's segmentation, the idea that we need to take large input documents and convert them to multiple smaller documents. Disentanglement is, in some sense, the opposite of that. So what we're looking at here is taking a sequence of relatively short messages and then building a set of multiple documents from those many, many short messages, trying to build those documents so that we capture the related messages together. The messages might be coming from things, as I've mentioned, like Slack channels, Microsoft Teams chats, speech utterances, things like that. The essential way that we're looking at doing this now is that we maintain a set of open documents, and then for each incoming message in the stream, we match the incoming message against each open document, again using some kind of way to do that matching, perhaps a vector embedding represented with a vector representing each open document. And then we can use content. We can also use things like content, metadata, the timing as well, with respect to previous messages. And what we do then is we say, OK, if there's no existing open document that's a good enough match, we'll open a new document. And then we can close a document once it's been idle for long enough. And when we close a document, we say, right, that bit of the conversation is finished. We'll take that input now and we'll put it into the knowledge pack. We can ingest that document at that point. And this allows us to build vectors that represent related parts of a chat session in such a way that we can index back into the chat session to recover that sort of context and that information in the response to a query. So that was a few words about what we do in terms of extracting content, extracting documents from input text. I'll turn now to embedding. So this is the process of taking text, taking documents, and representing them as vectors. The sort of the essential observation here, I guess, comes from linguistics in the late 50s. So the way it's often phrased is that you shall know a word by the company it keeps. That's the quote from that paper by Firth. So essentially what we're going to do is we're going to take words, we're going to represent them as vectors and combine those vectors to then represent documents as vectors. A very naive way of doing this might be to use what's called a one-hot encoding. So that's simply where you have a vector that indicates the word. So looking in the table on the right there, we have 3 words, Ronaldo, Messi, and DiCaprio, representing various superstars. And then we might, in a one-hot encoding, we're simply going to have a vector that represents, each component represents, is this Ronaldo, is this Messi, is this DiCaprio? So the vector for the word Ronaldo would be 100, the vector for the word Messi would be 010, and so on. That's fine, but it doesn't do anything to take account of the statistics of how those words are used in practice. Something like TF-IDF starts to add weightings to that. So you might say, well, words that are either uncommon or they're very localized perhaps give us more information in some sense than words that are very common and found in all the documents that we're considering. But even if you start doing that, it does give you more information, but it doesn't give you relationship information. It doesn't tell you anything about how, the vectors don't tell you anything about how 2 words relate to each other. And what we'd really like to be able to do is to be able to say, OK, I can compare the vectors, and that tells me something about the words that we use to generate those vectors. So instead, we might turn to feature-based encoding. So we're now going to have the columns representing some kind of meaning, some kind of feature. So instead of it just being is Ronaldo, is Messi, is DiCaprio as the column headings, the table here is showing is footballer, is actor. For fans of, well, I won't say anything about those particular footballs and those relationships. So what we're doing here is we're starting to encode relationships. Ronaldo here and Messi are both have a 1 in the is footballer column, so they're both represented by the vector 10. Whereas DiCaprio is represented by the vector 01, having a 0 in the is footballer column and a 1 in the is actor column. So we're now encoding relationships. We can see when we plot these vectors that both Messi and Ronaldo have ended up in the same place. So they are clearly both footballers in this case. And DiCaprio has ended up somewhere away, so because he's an actor and not a footballer. So we're encoding relationship information. The problem is that the dimensionality is going to explode. All possible features that we could possibly encode here will give us extremely high dimensional vectors, and that's not really very practical. So how do we handle that? So essentially what has been done over the last quite a number of years now is to start to use effectively the statistics of how words are used in conjunction with each other. So this idea that you know a word by the company it keeps, by the other words used around it. You train a neural network of some kind using very large corpuses of input text. And what that is basically doing is capturing the statistical information about how these things are used. And then when you constrain the number of output dimensions, you feed a word vector into the model on the input side, on the input there, and you get some output. And that output is going to be a vector. It's going to be a vector that represents, in some sense, the words that were fed into it. So you're sort of compressing the number of features down. What you end up with is that the features, the components of the vector, don't have such clear meaning anymore. It's not is footballer, is actor. But on the other hand, you have a lot of information encoded there in quite a compact form. So the sort of thing being shown here on the left, the figure on the bottom left, we've got various words on the input side. And when those words are seen in the input, they kind of cause inputs to feed through the network, go through various hidden layers. Could be more complex structures than this, obviously. And then certain output layer components light up. So when you feed king and queen in, you find that royal, palace, kingdom, these are all words that are lighting up as being related to both king and queen. We also have this useful behavior that there are relationships between the vectors that are preserved. So for example, if you look at how you might translate the vector for the word man to the vector for the word woman, and the same vector for the word uncle to the vector for the word aunt, and the vector for the word king and the vector for the word queen, those translations are all very similar. So in some sense, that translation is representing some kind of notion of gender. Those terms are related to each other. So now you've got a now you've got a representation that preserves these relationships to an extent and lets you start to do some interesting things with it. We can actually go further. So something like fast text, which is one of the processes that we use, one of the vector embedding processes that we use, which is getting relatively old now, but we still find it quite useful because it's quite fast in particular. If you have language with a large vocabulary and many rare words, what you often find is that you'll drop those words that are outside your vocabulary. So if the vocabulary is too big, you might use a subset of that, and you just simply drop the words when you receive them if they're not in the vocabulary. One of the things that fast text does that's interesting is by representing a word as a bag, a collection of character n-grams, so sub-words, if you like, each of those gets an associated vector, and you can then sum those up to give the vector that represents the whole word. What this means is you can compute vectors for out-of-vocabulary words if some of the subwords are in the vocabulary, and it also gives you the opportunity to improve the accuracy if words get misspelt. You don't just have to match precisely on the word you're given. You can construct a vector that represents the misspelt word, and that vector will be quite close to the vector representing the correctly spelt word. So as a quick example here, if you put those three words, asparagus, Pidgey, and yellow, through the fast text system, you get these vectors coming out. So these are a truncated version of those vectors. I mentioned this gives you the property that the more similar the documents, the closer the vectors, and that property works through analogies and misspellings. So here on the left, again from fast text, you can look at query word asparagus, and you find the closest matching words, the most similar, those scores represent similarity, words in the data set there. Beetroot, tomato, horseradish, spinach, all forms of vegetable being close to asparagus in some sense. It works for analogies as well. If you look at the query triplet here, again, another example from fast text, where you're looking at essentially word A minus the word B plus the word C, or rather the vector for the word A minus the vector for the word B plus the vector for the word C. If you feed in Berlin, Germany, and France, then Berlin minus Germany plus France gives you Paris as the most closely matching result. Then finally, we can see on the right an example where we've got a misspelt word, environment versus environment, but we're still coming up with quite relevant, quite related words as the most closely matching words in that data set. Again, because we can construct a vector that represents that misspelt word, and that vector is really quite close to the vector that would represent the correctly spelled word. Everything so far has been talking about individual words. So what we then need to do is combine these word vectors to create document vectors. And this is usually done fairly simplistically, looking, for example, just for the weighted average. And then I've mentioned similarity a few times. So typically we're looking at similarity as the cosine similarity. So essentially this is looking at the angle between the two vectors rather than taking the length of the vectors into account. We normalize that out. And so what we end up with, these are some screenshots from some debug output from the back end of our system. We can take something like a piece of text here. We can then translate that into a set of tokens here. We then convert that into a bag of words representation, which is encoded here. Then the final output is this big box on the right-hand side with lots of numbers in, and that's the vector representing, or a snippet of the vector representing that input document. I've talked a lot about how we use fast text to do this. That is one of these so-called large language models. There are now many of these, GPT-2, 3, Lambda. I think Lambda was the one that a Google engineer referred to as being sentient a few months ago. So there are lots of these now. Another one that we're actually starting to use alongside fast text, which, as I said, has quite a useful point in the space in terms of being fairly accurate, quite nicely general, and also quite fast. So we're looking at using sentence BERT. So BERT stands for bidirectional encoded representations from transformers, and it's essentially a different kind of structure to the statistical model that you build. It gives a significant improvement over the sort of more traditional recurrent neural networks when you're doing language tasks, essentially because you can use information from more than just the most recent words, or at least you're not forgetting so much of the information from the words in the past. And you're also able to start using information from words around the word you're interested in, rather than treating it just as a sequence of words that you're feeding in one by one. Finally, sentence BERT also uses positional encoding, so you actually include sequence information as well as simply presence or absence and frequency of words. The net effect of that is that you have something which is more computationally intensive. We're finding in practice it's several times slower than using fast text, but it is a lot more accurate. It's particularly with very short documents, where you kind of need to use the extra information you've got by the sequence information in the sentence. If you have a large document, then kind of the raw statistics of just which words are being used and how frequently might well be enough and give you quite good results. But when you start using very short documents where you're looking at maybe just a couple of sentences, it's quite useful to use the extra information that you have in terms of the ordering of the words in a sentence. So that was a little bit about embedding, vector embedding, the process of taking text, taking a document and representing it as a high dimensional vector. Having done that, we will have a collection of many, many vectors. In the case of Wikipedia, maybe 6 million vectors. So the challenge then is to start trying to find the most relevant vectors, the most closely related the vectors that represent the most closely related documents. As I mentioned, when we go through this embedding process, we have a nice property that two vectors that are close together are going to represent closely related documents. And so what we're looking to do is find the closest vectors to the vector that represents our query document. And to do that, we need to build indexes that enable us to do nearest neighbour search, so we can try and find things that are nearby to the query document. One way to do this, the way that we take, is using a system called MRPT, multiple random projection trees. What you're essentially doing here, I'll argue slightly by analogy, or explain slightly by analogy. You imagine you've got a large collection of vectors. So here the X's in the colourful boxes are vectors in the two-dimensional space. In practice, obviously, we're working in much higher dimensional spaces than that, typically 300, or in the case of SBERT, 760 something. What we want to do is we pick a random vector, we project all the vectors in the space onto that random vector, and we can use that to try to separate out the vectors in the space into two halves. Shown in the left-hand figure here with the green segment and the blue segment. So that's separated all the vectors in the space out into two parts. What we would then do is take each of those parts and repeat the same process with another random vector. So we're going to subdivide each part again, and that we're showing here. So we've taken the top green part, we've now got the green part and an orange part. Then the bottom blue part, we've now got the light blue part and the purple part. And we keep doing that recursively until we get down to probably some minimum number of vectors existing in each of these segments, perhaps 8, something like that. What we can do with that data structure that we've effectively built is that's a search tree, it's a binary search tree. So you would be able to take a vector that represents your query and then walk down that binary tree and figure out which of those segments contains or is containing the vector that you've got for the query. And you would then expect that the other vectors in that segment are going to be those that are closest to your query vector. Unless you're unlucky and your query vector is very close to the edge of that segment, in which case there might be vectors in an adjacent segment which are in fact closer than the ones in the segment you've ended up in. So you walk down this, you might walk down this tree, starting at the top, and you come down something like this, and you end up with these vectors here, these 8 vectors here in this dot, this node, and you say, well, those are the closest. But it might be that actually 1 or 2 of the 4 next door are in fact slightly closer. And that would be the risk, because you've made a random projection and you don't know, you pick the random vectors to project against each time, you don't know where those are going to land. So you might get unlucky. MRPT essentially does this multiple times. So you don't just build one of these trees, you build a lot of these trees by taking lots of different random projection vectors. And then you can search all those trees in parallel, and then you end up finding the set of vectors which are closest, and because they appear in multiple of the leaf nodes that you end up at. So when you projected multiple times using different random vectors and you're still finding the same things as being close, you can basically say, well, these really are probably quite close. I'm not going to get that unlucky if I do this many, many times. So that's the way that we build these data structures that let us do these searches very fast. There are lots of different ways of doing this. There are, well, lots, a dozen perhaps, different ways of doing this sort of thing. So different vector search algorithms. Another approach, for example, is called hierarchical navigable small world, HNSW. So taking this figure on the right as an example, you might say that you might look at having a lot of vectors here represented by the nodes, the circles with the letters in, and you pick a random entry point at a very kind of coarse-grained level. So the level 2 here, we've only got a couple of the vectors out of the total set represented. We pick a random one and we try and move around the graph that's been created to find the closest one to our query node, our query vector, which will be sitting about here if we project upwards from the query. So sitting around here. So we start out at M and we end up going to H. There's nowhere to go that's closer, so we drop down a level. The next level down, there are rather more of the nodes are included. So now we can find somewhere that's perhaps a bit closer, in this case L. There's nowhere to go that's closer, so we drop down again, and now we can go from L, and we end up going to G, because that is closest to the query vector. And so we found the closest neighbour at that point. Each time we were doing that, we were only dealing with a subset of the vectors, so that we didn't have to deal with having too many, so it makes the search relatively fast. There are a number of other ways that we can do this that are completely different. So you might, for example, build a knowledge graph. So there's an example here on the left, where you've got a graph that represents the relationships between entities. So you're explicitly relating entities to each other, typically then using a graph database of some kind to then execute those queries. That's fine, but you have to challenge there that if you have something that you wish to search for which is not related to any of the entities, you have to do something to get that process started. You could also just do traditional keyword search. As I've mentioned, that has its proper place in its proper application. It tends to be when you know what you're looking for to a greater extent than when you're just trying to do this generalized discovery process. Having done that, the next challenge then obviously is to scale this up to bigger and bigger haystacks, bigger and bigger collections of vectors. As the data sets get bigger and more complex, one of the nice things with MRPT is that it's very straightforward to split data across multiple indexes. You just build multiple MRPT indexes for subsets of the data, search them all in parallel, and then because you're looking at essentially similarity, effectively distance to some extent in the space, as I mentioned, the difference in angle between vectors perhaps, you can very easily combine results from different data sets because all the vectors are created in the same way, they're all consistent. And so you can find the top 10 across multiple knowledge packs and merge those together to get the top 10 across all of the knowledge packs combined. This means that we have a lot of deployment flexibility in our platform. We're able to split data across different knowledge packs according to different business needs. So for example, it might be the security clearance required to see some results. Some people don't get to even know that that data exists because it's in a knowledge pack they don't have access to. We can split data sets that get too big for the nodes they're deployed to, split them across many nodes. And we can scale this horizontally just by deploying more nodes, making the cluster bigger. We also have the capability, because of the way the platform's been architected, that we can trade off different embeddings. So we don't have to say this is the only embedding you use. And equally, we don't have to say you have to come up with your own embedding and just turn up with some vectors. You can give us documents and we can use a range of different embeddings to give us different trade-offs in terms of the vectors that are produced. So, for example, as I've mentioned, fast text is quite fast. It produces, not in the default configuration, vectors that are not too big, and it's reasonably accurate. It's perhaps not the most accurate, as I said, particularly with very small input documents, but it does a pretty good job in the general case. SentenceBird, on the other hand, we're finding it does use more information, so it does give you greater accuracy, particularly with shorter documents, but it is quite a lot slower. I mentioned, I'm not going to say too much about this because of time, but essentially, although we default to English when we're supporting this, we can support many different languages. If you do a bit of work to align the embeddings that you're using, then it is possible to create vector spaces that are compatible, but are dealing with documents in different languages. So you can take an English language document and use it to search a knowledge pack that was created from documents written in Arabic, for example, and find the most closely related results without having to actually do translation between those documents between those different languages. As I mentioned, there are alternatives to MRPT, other ways of doing approximate nearest neighbours search that provide for other kinds of feature sets and so forth. But MRPT, we've found so far, does have a good combination of performance and scaling. So that's how we do indexing. That's how we actually go about enabling you to find the right results, having done the embeddings, having extracted the documents. I'll talk finally now about the integration, the way we enable this technology to be integrated into existing tools and workflows in a fairly frictionless fashion. So what we have is we have a platform, as I mentioned, a SaaS platform with a number of REST APIs, public-facing REST APIs that allow customers to access back-end functionality. The two core APIs really are the ingestion and query APIs. So the ingest API is used by connectors to enable knowledge pack contents to be updated and knowledge packs to be created. So this is how you put data into a knowledge pack. An example of this kind of thing would be a SharePoint connector. So I'll say a bit about that in a second, but essentially something that you would connect to your SharePoint and it's able to go in and pull out the data, pull out the documents, and put them into our system and create a knowledge pack from those. The query API is used by extensions to make the integration of this query capability very straightforward. And it's actually quite important that it's done like this. So rather than building a separate tool that you would go to execute your queries typically, what we're really looking to do is make this as frictionless as possible. So we need this capability to be added to some existing tool and existing workflow that you use. And that means that we get access to, by doing that, we get access to some document that represents what you're doing. And so we can now feed you proactively the relevant content from the knowledge packs you're searching. So an example of this would be our web components. I've got some screenshots in a second. First, to talk about connectors. So these run outside of our middleware. They run outside the API, so they access the public-facing API. Commonly, we might run them on our cluster, so we're running them on behalf of customers, but they might equally be run by the customer on their own resources and just talk to our APIs. We have connectors to public data sources, so that might be websites such as archive, so we're updating that using the RSS feed that they helpfully provide. We might use Apollo, which is the Cambridge University Library open access repository. So we're doing that by looking at the sitemap and how their sitemap evolves. So there's multiple different ways of building these. They can also include private sources, as I mentioned, such as SharePoint. So we've worked with one customer there. We've got a connector running against one of their SharePoint sites, and we can support the authentication thereby using integration with their Azure ADFS setup. We've also got the capacity to kind of use a sort of multi-layer thing here. Multi-layer approach here. So we look at taking framework content where you might say, okay, rather than looking at all the documents in this SharePoint, we're essentially going to give you an index. We have an index spreadsheet typically, which then describes each document that we should go and fetch. The connector should go and fetch from the SharePoint and provides all the metadata associated. That's useful when we're looking at building a knowledge pack, which might be relatively small. Could, for example, one of the customers we work with, we're using the UN Sustainable Development Goals. So we have a document representing each goal, a document representing each target. That's fewer than 150 documents. But that describes a framework, and that's then a useful thing to be able to match other content against to see which parts of that framework that other content is most closely related to. I mentioned extensions and having sort of web components and such like. So we have a range of extensions that embed the query API. So you don't have to talk directly to our API if you don't want to. You can use these extensions to add this capacity into existing systems. By far, the dominant mechanism for deploying these is some kind of single-page web app. So you essentially provide some HTML, or we provide some HTML, some CSS that you can then customize, and some JavaScript. And that enables you to embed this capacity into websites and applications. So the screenshot here on the left is from the advanced search page on the University of Cambridge Apollo site. So this screenshot here is showing our web components here. I've used the URL of our website as the query term, and the text from that's been fetched. And here are the results that came back, sorted by relevance in this case. And that took a couple of hours, I think, to add that to the website. It was just a little bit of HTML, a couple of lines of HTML that had to be added. Very similar code, in fact, is used to provide the Chrome plugin that we have. We have an add-in for Microsoft Word. So these sorts of things here. So this is an example on the left here of Apollo where you're looking at a particular record, a page about a particular article, and then that is used as the query term. So we're now able to provide you with the relevant other content from inside Apollo and Archive. We have this example here in the middle of the screen, which is the Chrome plugin. It can be installed from the Chrome App Store, where we're looking at using the current web page. So in this case, again, I'm using our home page as the query term there. Then finally, in the bottom right, we've got a plugin which is not yet publicly released. We have a plugin for Microsoft Word. So this is a Microsoft Word add-in that uses the content that you're typing into Word as the search term or as a query term, and is able then to provide you with relevant content on the right. And with that, I'll finish. Back to John.
Thanks, Mort. That was fascinating. So really now want to open this up to question and answers. So if you do have any questions for Mort, you can either raise your hand or probably better if you can type something into the chat window, and we'll try our best to answer your questions. As people are thinking about what questions they may want to answer, may ask even, and us to answer, just point out this is a two-part seminar series. So we've got Mort doing a more academic technical overview, and then next week we'll have Ian Firth, who's our Chief Product Officer, who will be going over more practical implementations of this technology and just showing some real world use cases about how different organizations have used this and how it's actually making a difference to their organizations. So if you're interested in that webinar, then the details you can get to through our website, so ikva.ai/webinars, where you can sign up, and it is another Eventbrite seminar. And that'll be this time next week, so Thursday the 6th of October at 3:30. So again, if you have any questions, then please either raise your hand or so we can unmute you, you can actually ask them, or alternatively just type them into the chat window. Mort, is there anything else you want to say about some of the amazing technology we've got at the back end in terms of particularly about, you mentioned vector graphs or graph technologies?
I think, well, I could just very briefly say how it's all deployed. So we have Kubernetes clusters on which this content is deployed, this technology is deployed. We're using a service mesh architecture to interconnect everything, which gives us a lot of flexibility as to how we can pick up and use different components to add them into the system.
And we have a question from Carlos. How do you measure the accuracy of discovery and search?
That's quite a common question, quite a subtle one. So one thing we've done is we've tried to benchmark against data sets where the outcomes are essentially known. And doing that, we can say that these are the documents that a human scoring process has determined to be the most similar to the documents that you've got, the query document you put in. And on those kind of benchmarks, we do quite well because we are able to use all the content of the document. It's actually quite difficult to do that well for very large data sets, because if you think about something like Wikipedia, you can try and make inferences about which pages might be most closely related to each other. Maybe you did the same for Archive, 3 million academic preprint PDFs. You can try and make inferences about which of those are most closely related to each other, but it's quite difficult to have humans go through and actually score the complete matrix of all 3 million of those. So what we instead find that we've done, and there's a little bit done in one of the early scientific papers that was published about, one of the academic papers published about this process, is essentially using user studies. So you have some people sit down, they know a bit about the data, they know the query documents, and they look through the results and they say, yes, that's a relevant result, that's not a relevant result, and use that kind of scoring process to try and do the measurement.
So, Carlos, it's probably also worth saying we have done some benchmarking against what we call the gold standard data set. So, as Mort was saying, some of the data sets that are out there where humans have gone through and said what's relevant, and we've matched our results against what humans have said is relevant. So, if you're interested in seeing that data, you can drop us an email at some of the contact information we've got here, and we can send you the results of those benchmarking tests.
Yeah. Actually, one thing I should also say, because it's a sort of interesting feature of that sort of process, is that it can be quite subtle as to what's most closely related. So one of the things I think is interesting about this discovery versus a more traditional search approach is that we're able to overcome some of the unconscious bias that arises when you've got an expert who knows the field and they know the content and they know the documents, and they interpret a document, a query document, in a particular way, and they say, therefore, that query document must be related to these input documents. But they brought their own interpretation to that. And it may well be that somebody else would look at that and say, well, actually, I'm going to interpret that document slightly differently. And I say it should be related to these other documents instead. One of the nice things about this discovery approach is because we're using all the words in the document, all the content in the document, there will still be biases depending on how the fast text models or whichever other language model was being used, depending on how that was trained. But hopefully those input data sets were large enough, and if they were done properly, representative, if you like, enough of a large corpus of text, that you kind of overcome that unconscious bias of sort of knowing what you're looking for when you go into the search problem.
Okay, thanks, Mort. I have a question which came in by email a little bit earlier, which was vector search seems to be the new kid on the block, and there seems to be a few different people looking at it. Why is this all of a sudden raised to prominence?
That's a good question. It's always a bit hard to know why these things have happened. I would say that over the last few years, I think it's a combination of people having built and then made openly available these kind of large language models that lets you do these embeddings in a reasonably fast, reasonably accurate way. I think that the increasing rate at which sort of APIs are available to let you plug into different systems then makes it very interesting how you can start to apply some of these technologies. So they sort of move out of the lab, if you like, move out of the data science domain and can be made more generally applicable, which is essentially what we're trying to do.
Cool. Thanks, Mort. Let's just give a couple more seconds. So Nicholas has a question. How would you avoid entropy making the vectors random samples of randomness on large data sets, thus not distinguishing concepts?
That's essentially part of the training process, I think, of how the language model is built. So if you've taken the corpus that you're going to use to train your language model from sort of real uses of real language, so you've got the statistics are in some sense, we use the word representative in a slightly non-technical sense, but in some sense representative of the use of language. Then the process of ingesting that corpus data and using it for training will hopefully make sure that what you end up with is a statistical model that in some sense encodes real information about how language is used. And so that means that the vectors that you get out won't just be random. They should actually represent, as I said, you end up with something where the concepts are represented well in the vectors. So two vectors close together do actually represent two words that are used in similar contexts. Coming back to that idea that you know a word by the company it keeps. In some sense, you can kind of define the meaning of a word by all the other words that you find around it and the words you don't find around it.
Okay. Thanks, Mort. Nicholas, I hope that answered your question there. If you want to follow up, then you can raise your hand and we can do that. No worries. Thanks, Nicholas. I'll just give a couple of seconds for to see if anybody else has any more questions or comments that they'd like to ask. Just as a quick reminder, we have recorded this, so we will be distributing the details of this recording. So if you want to go back and have a look at it, you'll be able to do that. Likewise, if you want to pass this on to any of your friends or colleagues, then you'll be able to do that as well. Cool. Okay, I think since there doesn't seem to be any more questions at the moment, I think we'll say thank you to Mort for doing this webinar. Thanks to everybody else that's been on this call for joining us. If you do need more information, you've got all the contact details there. So feel free to contact us, and we'll be happy to answer your questions or give you any more information that you need. Cool. So thanks a lot, everyone, and wish you a good rest of the day. Okay. Thank you.